Yeah, thank you so much for the introduction. I'm Kevin Loughlin. This is work I did at the University of Michigan with my lovely collaborators from Michigan, Microsoft, Carnegie Mellon University, and the University of Washington. And it's on a hypervisor Siloz that leverages something called DRAM isolation domains to prevent inter-VM Rowhammer. So inter-VM Rowhammer, to understand that, we first need to understand just life in the cloud amongst these different VMs. And so routine multi-tenant life in the cloud is such that we have a shared physical machine, and atop that physical machine, we have a couple of virtual machines. We'll call them 0 and 1, but for a little more fun and concreteness in this talk, we'll call them Kevin's virtual machine, my own, and my advisor Baris's virtual machine. Now, when all is going perfectly in the cloud, we're sharing nicely, performance is perfect for everyone, security and isolation is perfect for everyone. But as we all know, that's not how life actually works in the cloud. And indeed, instead we'll have rogue actors, such as the occasional evil Baris out in the world, who decides that they want to do things such as try and corrupt the state of my VM. And what he'll do in this example is he'll corrupt my profile picture such that now my smiling face is replaced by some sort of pixelated caterpillar ruining it. And so you might ask, how on earth is this possible in the cloud? Well, there are a variety of vectors, but the one that we're going to talk about today that's unsolved and very prominent is Rowhammer bit flips. We don't need to understand exactly how Rowhammer bit flips work right now. All we need to know is that if you access DRAM above a certain rate, you risk bit flips in nearby locations of DRAM. And so why Rowhammer is such a concerning problem is particularly because the susceptibility to it is literally getting worse. As we look on the y-axis here, we have the threshold of access rate that you need to surpass in order to see Rowhammer bit flips. And as we compare from older DRAM to newer DRAM, the threshold is actually lowering. So it's easier to flip bits in newer DRAM than in older DRAM. And these bit flips manifest at the system level as very problematic things such as data loss, machine failures, and even privilege escalation, the complete subversion of machine. So there are two more concerning factors, of course. The first is that today's systems are literally already vulnerable. So the situation is getting worse, and we're starting in a place where we're already vulnerable to these bit flips. And the second factor is that access patterns that actually flip bits are continuing to emerge. So there was the initial Rowhammer pattern, but even during the publication of this paper, and when we made the talk's title Inter-VM Rowhammer, a new phenomenon called row press came out that flips bits in a slightly different way, but still relying on the fundamental principle of nearby DRAM locations. So of course, with increasing susceptibility, we risk more and more bit flips, and as we see here, my picture becomes more and more corrupted until we end up in the absolute worst case, which is that my machine is entirely subverted and now shows an embarrassing picture of myself from freshman soccer in high school. And I think we can all agree that we'd love to avoid this case, and while this particular case might be slightly humorous, what's absolutely not humorous is the fact that today's cloud DRAM lacks strong isolation. And so the motivation for today's talk is that different tenants or virtual machines can interfere with each other in DRAM. And this leads to security problems like Rowhammer that we've talked about so far, but it also leads to things like performance contention that I'm not going to get into in today's talk, but that we believe our work is applicable to going forward. So the two key contributions, the first of these are that we introduce the isolation primitive of subarray groups for DRAM isolation domains. And subarray groups are a structure that prevent inter-VM bit flips without sacrificing performance, crucially, in order to make them practical. The second key contribution is that we introduce the Siloz hypervisor that uses these subarray groups for management of memory. And in doing so, this work provides the first step towards practical management of DRAM as isolated domains. So if you take one thing away from today's talk, this paper is all about per-tenant DRAM isolation, bringing the management of cloud DRAM in line with that of other hardware resources that we do today. In the remainder of this talk, I'm going to first talk about what exactly it is we want in an isolation primitive and why we don't have it. I'm then going to go into the subarray group primitive itself, how the Siloz hypervisor uses that primitive, and finally the evaluation. And since I like memes, we'll start off with what we want being a meme. What we want specifically is high-performance DRAM isolation domains, and we've wanted these since, of course, yesterday. So what this really highlights is the fact that in today's DRAM structures, performance is achieved at the expense of isolation. So if we look at a typical DRAM system, we have a CPU hooked up to a few DRAM modules, and each of these DRAM modules breaks down into a row column structure known as a bank. So that's the DRAM architecture, And what's crucial here is that different banks can be accessed in parallel. And so in order to actually reap the benefit of this performance feature, different pages of memory are interleaved or spread, or you can think of them as split, across different banks of DRAM. So we had in the previous talk that workloads can be DRAM bandwidth bound. This is how you get better bandwidth out of your DRAM. You actually split your page across multiple banks such that common access patterns can achieve accesses to bank 0, 1, 2, and 3 in parallel. The downside, of course, here is that we've talked thus far about how having nearby pages, pages from different isolation domains nearby in memory exposes them to Rowhammer bit flips. So if page A belonging to one tenant activates DRAM above a Rowhammer threshold, we can now experience bit flips in another page potentially belonging to another security domain. So altogether, this means that our primitive needs to have two properties in light of multi-tenant isolation here. The first is that we want performance by allowing page interleaving across banks. In order to be able to fully realize and fully use our DRAM bandwidth, we must have DRAM bank level parallelism, or we're dead in the water for practicality. The second feature that we of course want, given the title of this talk, is isolation among different VMs in DRAM. And this is our key security property, and it wants to look something like we have on screen here with some sort of barrier between the different domains. But crucially, we want to do this without wasting DRAM. So you could imagine a world in which we just inserted a bunch of unused guard rows in between different domains or in between different memory, but that would of course just eat up the available DRAM available to us, in the worst case incurring 50% more overhead in the system. So instead, what we propose to do is to use something called the subarray group primitive, which begs the question of what exactly is a subarray. Well, it turns out that just as DRAM modules are architected and presented as sets of banks, each bank underneath the hood, while it's exposed to software as a single row column structure, is in fact implemented as a set of subarrays. These subarrays aren't directly exposed in today's hardware, but they are visible with reverse engineering and experimentation, and they have a really nice property, which is that they provide Rowhammer isolation as confirmed in prior work. And roughly speaking, this is because each subarray is separated physically in hardware by I/O circuitry. So if we look at two different VMs on two different subarrays, if the first VM hammers DRAM, the second VM is isolated from those bit flips. So we can clearly see how subarrays provide the isolation property that we want. What we haven't seen yet is the performance. And the way that we achieve that performance is by grouping these subarrays to exploit bank-level parallelism. A subarray group in particular is composed of a subarray from each bank. So if we take these VMs and we isolate them according to this principle, the 0th subarray group takes the 0th subarray from each bank, the first subarray group takes the first subarray from each bank, and so on and so forth. So now we've combined to have two really nice properties. First is that each tenant here has subarray level isolation. No two tenants are co-located on the same subarrays. Second, from a performance standpoint, each tenant can still use every bank in the system, so they can exploit full bank level parallelism and maximize their DRAM bandwidth. A natural question with this primitive in place is just how big are these things? Well, as with many things in life, the answer is, of course, it depends, but I can tell you exactly what it depends on, and I can tell you in our reference implementation what the size is. So the subarray group size is a product of three system factors. The first is the number of banks that you actually interleave a page of memory across. And in our system, that's 192, a popular major cloud provider Skylake server configuration. The number of rows per subarray, which in our reference DIMMs is 1024, and the row size, which is pretty fixed across DIMMs these days, and that's 8 kilobytes. So multiplying these three factors together, by default on our system, we get 1.5 gigabyte subarray groups. I will note that finer-grained subarray groups are absolutely possible, and while I don't have time to get into the factors that affect them in the 17 minutes for this talk today, we go into a lot of discussion in the paper on how to actually achieve finer-grained subarray groups for different use cases. Okay, so with the primitive in place, we're going to talk about the design of the Siloz hypervisor and how it actually uses subarray groups. Perhaps unsurprisingly, what Siloz does is it places different VMs into private subarray groups. And it does this according to an existing property of VM pages called mediation status. So it turns out that VM pages either belong to unmediated classifications or mediated, where unmediated simply means that the guest can access the page without trapping to the host. And this is actually the vast majority of guest memory. This is what we want for performance so that we don't have to have the host intervene on access. Of course, what this means is that unmediated pages can be trivially hammered by the guest in DRAM. And so as a result of that, we put these unmediated pages in their own private subarray groups per tenant. In contrast with mediated pages, they actually trapped the host on all accesses. So you can think of something like emulated devices as being in these pages for virtualization. And so for these pages, the host is literally performing all of the accesses on behalf of the guest, and therefore can either trivially rate limit attempted hammering or apply its own policy, and therefore these pages can be put with host reserved data in their own subarray groups there. The way that Siloz actually provisions these subarray groups to different virtual machines, if you recall, our requirement here is that Siloz needs to manage DRAM as subarray group partitions. And it turns out that we actually have something really nice in Linux for managing memory partitions already, and that is NUMA. So existing NUMA support, non-uniform memory architecture, basically says that if I have a couple of sockets, each with their own memory, that I can manage socket 0 as a pool and socket 1 as a pool, and I can assign certain processes, certain virtual machines, socket by socket, and control access that way. And so rather than reinvent the wheel with Siloz here, we simply abstract a logical NUMA layer atop this physical NUMA layer and maintain a mapping so that we can preserve the original physical NUMA optimizations. And so what happens here is that each subarray group is simply presented as a logical NUMA node that can now be assigned to a guest and reuse the rich and robust infrastructure that Linux has in place for managing NUMA nodes. One remaining question here is whether isolation is enough for, in particular for a structure called extended page tables or EPTs. You may wonder what makes these structures so special. Why am I specifically going into detail about them? Well, as we see on screen here, extended page tables are what literally defines what addresses that a guest can access. So they map guest addresses to host addresses, and since host addresses correspond to subarray groups, effectively the extended page tables define and enforce the subarray group mapping. So this is problematic for the following reason. Subarray groups contain, but they do not prevent bit flips. So for this specific goal of inter-VM isolation against inter-VM Rowhammer bit flips, we know that EPTs store the subarray group mapping, and so if we have a corruption in an EPT entry due to a Rowhammer bit flip, we can actually flip the subarray group that we point to and break out of our subarray group sandbox. So otherwise, in other words, bit flips and EPTs can actually completely compromise subarray group isolation. And so as a result of that, we provide supplemental protection specifically to EPTs to actually prevent bit flips rather than just contain them on a per VM basis. And the technique we use here is going back to an earlier portion of this talk where I mentioned guard rows. You may recall that I said we don't want to pervasively use guard rows because they eat up so much DRAM and can incur high overhead. But the reason that they work here is that EPTs occupy a very small portion of memory. And so because they only occupy a very small portion of memory and their overhead is relative to how much memory you're actually occupying here, the EPTs and guard rows altogether only require reserving 0.024% of DRAM. In other words, we can use 99.75% of DRAM pervasively just how we want it for general purpose usage. So to recap the design of Siloz, Siloz places virtual machines in private subarray groups. It manages those subarray groups via logical NUMA nodes, and it protects the subarray group mapping stored in extended page tables via guard rows. One thing I do want to note is that in a DRAM module itself, there's actually another layer of remapping possible called DIM internal remaps. I don't have time to talk about it today, but we have a whole section in the paper on when this happens, why it happens, and why it isn't a problem for our solution. So to conclude, I'm going to go into the evaluation details, and our methodology is as follows. We implemented Siloz in a Linux KVM implementation, and as a result of that, we evaluated it against an Ubuntu baseline. The host machine that we evaluated on is a major cloud provider Intel Skylake server configuration. And we verified the security properties of Siloz, namely that it prevents bit flips in EPTs, as well as contains bit flips otherwise to the subarray group in use, using the Blacksmith Rowhammer fuzzer. This is the state-of-the-art bit flip finder, if you will. So it surpasses the latest defenses in order to flip bits. And what I am going to get into a little bit more here is the performance evaluation, where we measured Siloz's effect on a variety of workloads, such as cloud workloads like memcached, the Intel memory latency checker, and synthetic workloads like spec and parsec. So if you recall, the whole point of our design was to have negligible impact on performance while still achieving security. And so here we're going to show Siloz's effect on execution time normalized to the baseline in orange. And as we see, for all of the different workloads we ran, we never saw more than a plus or minus 1% difference. And in the vast majority of these cases, this was all within confidence intervals here. So effectively, the takeaway here is that Siloz has very negligible impact on execution time. You may, of course, wonder, why would it even have an impact plus or minus in the first place? So here, one factor as to why Siloz could potentially increase execution time or worsen execution time is that we are increasing the number of NUMA nodes in the system, effectively speaking. And so for certain things like memory allocations, we potentially now have to iterate over a greater number of NUMA nodes. But we were able to avoid that overhead in the vast majority of scenarios by the mere fact that, for example, if a guest is only allocated 2 subarray groups or 2 nodes, we know that the allocations will only ever come from that region, and we can avoid the vast majority of those iterations. In contrast, where Siloz can actually help with performance is the fact that we apply more stringent NUMA locality constraints to the system. So one example is that we found that extended page tables in the baseline system are often allocated with poor NUMA locality, whereas in Siloz we enforce that much more stringently. So in a similar vein to execution time, we have throughput effects being negligible in the same vein, within plus or minus 1% for any individual benchmark. And you may recall that bank-level parallelism is how we actually exploit throughput. And so since we've designed this to not affect bank-level parallelism, we're able to maintain similar throughput levels. So to recap, the objective here was to prevent inter-VM Rowhammer with negligible effect on performance. The approach we took was isolating VMs to private subarray groups. The deliverable was a Linux KVM implementation that provides comprehensive protection with negligible impact on performance. And the broader impact of this talk, we believe, is that we provide the first step towards practically managing DRAM as a set of isolated domains. I'd like to thank my wonderful collaborators, Jonah Rosenblum, Stefan Saroiu, Alec Wolman, Dimitrios Skarlatos, and my advisor, Baris Kasikci. And with that, I'm happy to take your questions.
Questions? Yes, please.
Hi, great presentation. Ada Gavrilovska, Georgia Tech. Can you comment on the interplay with huge pages and if you're essentially doing a little bit more memory stranding here because you have all these memory domains, so all these extra NUMA domains. So did you look into those effects?
Yes, thank you. Thank you for the question. So there are 2 aspects here. The first is the page size. For the page size, because we were modeling a production cloud environment, we used huge pages. The effect of huge pages in this case doesn't so much affect your NUMA mapping as it does how much memory do you require to store your extended page tables. So we only evaluated with 2 megabyte pages. We didn't look beyond that. But it's an awesome avenue for future work. As for the memory stranding, this kind of goes into fragmentation, so I'm going to incorporate a little bit of a backup slide here. So I mentioned earlier that we could reduce the subarray group size to help avoid some of these problems with fragmentation or stranding. And so we have 3 factors that I mentioned earlier, the interleaved banks, rows per subarray, and row size. There are a variety of things you can do for each of these, but I'm going to talk today about what's already possible, which is changing BIOS settings with regards to interleaving across memory controllers. And in doing that, you can still reap the benefit of bank-level parallelism, but restrict memory controller parallelism. And the reason why this is considered acceptable is because we're kind of moving towards this with sub-NUMA and chiplets, where we want our accesses to be local to a specific memory controller for better latency at a slight throughput cost.
I have one more clarification. How many rows do you need to leave within if you wanted to prevent Rowhammer within a subarray?
Great question. So the answer is that it's rising. Today it's about 4 on each side on cloud systems. We actually did 16, 1 to be conservative against future applications, and 2 because there are certain dim properties about why you need 16 for safety measures. But yeah, roughly 4 today, and it's getting worse.
Thank you.
Okay, please. For level.
Sorry, the gentleman on the second floor. Right, thank you. Brad Karp from UCL, thank you for the talk. I just had a quick question about, it seems like the isolation granularity of the DRAM hardware seems to be a good fit for VMs, and you framed the problem as inter-VM isolation. Is there a threat intra-VM? Like, could there be some workload running inside of one VM that could be sort of abused for a Rowhammer attack inside of a VM? And is there any solace, does this hardware structure offer any help inside of a VM?
Yeah, great question. So the short answer is that there could potentially be intra-VM threats. So this work took the first step towards doing inter-VM, since that's the first order concern in many cases in the cloud. But within a VM, it is possible that you want to subdivide into different security domains. So maybe you're running a server and you don't trust your client or something along those lines. So things that you could do are you could either shrink down the subarray group sizes using some of the techniques we've talked about, or you could even subdivide your subarray groups using some sort of guardrails if you're willing to pay the DRAM cost. But ultimately, it's still an avenue for future work.
Thank you.
Phil Levis, Stanford and Google. So this is super neat how you're leveraging kind of the physical layout of the DRAM to do this isolation. But the question is, what I ask is, how stable is that? Because that's something which they could change at any time. I mean, how long has it been this way going forward?
Yeah.
I think about Flash, where they transitioned to having the addressing logic underneath the layers. And so do you have any sense about how stable this is from a microarchitectural standpoint?
Sure. So for stability, I can say that we're at DDR4 DIMMs that we evaluated on for this. DDR5 DIMMs have recently come out, and DDR3 DIMMs were before. All of these technologies use subarray, and in fact, across things like HBM, subarrays are in play too. There are a variety of reasons why subarrays are such useful structures, but I think it's very unlikely that subarrays will not continue to be used. Now, the specific mapping of pages within subarrays, the specific sizing, those things can change. We've seen a general trend in growth from about 512 up to maybe 2,000 rows per subarray. This is part of the reason why in this paper we advocate that this should be architecturally exposed, or we should at least expose memory isolation domains that are allowed to exploit these subarray structures, because there is no guarantee on the stability. Historically, it's been stable, but we would like to see it actually be guaranteed to be stable for practicality.
Okay, let's thank Kevin again for the fantastic talk.